Welcome to This Explainer. Whenever we look up at a modern city skyline, we're actually witnessing a massive heavyweight battle. In one corner, you've got human ambition and what we can call architectural ego, that sheer unrelenting drive to just build the tallest, most iconic tower possible. And in the other corner, the completely unforgiving laws of physics and economics. Let's call that structural logic. Today, we're going to unpack exactly what happens inside super tall skyscrapers when these two massive forces collide and uncover the hidden systems that keep these giants standing. So to kick things off, let's look at what engineers call the core-to-floor dilemma. Take a standard 20-story building. Notice how narrow that central core is? That leaves a ton of what developers call leasable square footage, the actual usable space that pays the rent. But then, look at a 100-story building. As a building gets taller, it needs way more elevators, much thicker walls, and heavier columns just to fight off gravity and wind. That central structural spine essentially acts like a parasite. It expands outward, eating up all that valuable rent-paying space. This dead space is the very first major penalty of going vertical. And the data behind this phenomenon is honestly pretty brutal. Recent multidimensional research into the spatial efficiency of over 150 tall buildings reveals a highly specific, quantifiable penalty. For every single meter a building rises, its spatial efficiency drops by roughly 0.078%. Now, I know that sounds like a tiny fraction, right? But spread that out over a massive 400-meter super tall, and you are losing huge percentages of your usable floor area strictly to mechanical and structural demands. You're literally paying to build more just to rent out proportionally less. Section 1. The vertical logistics penalty. Just getting thousands of people up into the clouds every single day without turning your entire floor plate into nothing but elevator shafts is an absolute engineering nightmare. So how do engineers solve this elevator penalty? Well, if you've ever worked in a super tall, you already know you don't just push a button for the 90th floor from the ground lobby. Modern towers use incredibly complex software known as destination dispatching systems. You enter your destination at the ground floor, hop on a high-speed express elevator, and then transfer at a mid-air sky lobby to a local elevator that takes you to your specific zone. Mathematically, this zoning strategy, often combined with double-decker elevator cars, is the absolute only way to keep everyone's wait times under 30 seconds without completely hollowing out the building. But the real bottleneck here is the physical material itself. Traditional elevators rely on really heavy steel ropes. In a super tall, almost 70% of the elevator system's total weight is just the cable. If you actually tried to run one continuous elevator shaft 100 stories straight up, those massive steel cables become so heavy they can't even support their own weight. They'd literally risk snapping. So physics basically forces engineers to break the journey up into segments. Section 2. Battling wind and sway. Okay, so once the engineers solve gravity and logistics, they run face first into an invisible, chaotic force that wants to tear the building apart. The big question is, how do you stop a skyscraper from swaying like a 19th century whaling boat? Well, above 10 stories or so, lateral wind loads get incredibly intense. A skyscraper with a high aspect ratio, meaning it's very tall and very skinny, essentially acts as a giant cantilever beam stuck in the ground, just reacting to violent wind shear. If you don't engineer for this, the people working at the very top are going to be totally miserable, maybe even physically ill from all that constant movement. To truly grasp what developers are up against, just check out the data from these wind tunnel tests for Chicago's 67-story Park Tower. This shows the massive overturning moments and bending forces acting right on the base of the building across 36 different wind directions. The wind is just constantly trying to bend and twist the structure. So to fight back and keep the building stable, structural engineers have developed a few absolute cheat codes. The first big cheat code is the outrigger system. Instead of just making the central core thicker with more concrete, which, as we discussed, eats up all that valuable rentable space, engineers use these giant structural trusses to link the core directly to the heavy perimeter columns on the outside. Think of it like a skier planting their poles really wide in the snow. It massively increases the building's overall stiffness and fights back against that terrifying sway. But what's wild is that sometimes just adding more rigid steel and concrete still isn't enough, or it just completely ruins the floor plan. And that is when structural logic deploys its ultimate secret weapon, the tuned mass damper, or TMD. It sounds super complex, but it's basically just a massive block of steel or concrete hidden up in the mechanical levels near the very top of the tower, specifically designed to mitigate those wind-induced oscillations.
Here's a brilliant example. This is the schematic for the Park Tower's 300-ton tuned mass damper system. It acts like a giant, hidden pendulum suspended by heavy cables. When a severe windstorm pushes the building in one direction, this massive 300-ton block actually swings in the exact opposite direction. It acts as an incredibly powerful, frictionless brake, pulling the building right back to its center point and neutralizing the sway before the people inside even notice it's happening. And the sheer precision involved here is amazing. The engineering goal is to keep the building's peak acceleration under 15 milli-G. That's a super strict standard set purely for occupant comfort. To pull that off, the Park Tower TMD uses military-grade, hermetically sealed hydraulic dampers that were originally approved for the U.S. space program. These cylinders absorb the wind's energy completely frictionlessly, require absolutely zero maintenance for the entire life of the building, and ensure that a resident sipping coffee on the 67th floor doesn't spill a single drop, even in the middle of a massive storm.
Section 3, the cost height curve. So we have these incredible engineering solutions that literally let us touch the sky, but they come at a very steep price. This is exactly where architectural ego smashes into the accountant's ledger. Look how rapidly and totally disproportionately these construction costs escalate. Based on historical data from Manhattan, building a 20-story structure costs roughly $400 per square foot. But the moment you push up to an 80-story building, that cost literally doubles to around $800 per square foot. The extra concrete for the foundation, the heavy steel for wind bracing, those complex zoned elevator systems, it all creates this brutal, steep upward curve in your per-floor costs the higher you go. And we see this exact same economic reality globally. Let's compare some staggering figures out of Dubai. A standard, structurally simple tower might cost somewhere between $730 and $1,500 per square meter to build. But an iconic, highly complex supertall like the Burj Khalifa, that price tag skyrockets to roughly $3,500 per square meter. In fact, research shows there's an average 8% cost escalation for every 10 floors you add to a building. Economically speaking, supertalls are wildly expensive and incredibly inefficient to build. Section 4, return on objective, which brings us to a pretty glaring contradiction. If structural logic, basic physics, and economics all prove that supertalls are terribly inefficient and shockingly expensive, why do developers keep building them? Why even bother? Well, listen to this quote directly from a spokesman for Emaar Properties. They're the developers behind the Burj Khalifa. More than the ROI for the individual buildings, it is the economic value and social prestige that supertall buildings create for the community that matter. That completely shifts our understanding, doesn't it? These megatowers are rarely built just to turn a direct return on investment profit. They actually serve as massive return on objective anchors. We're talking city branding, global tourism, and undeniable international prestige. And that reveals the real financial game being played here, 35 to 50%. That is the massive surge in value that developments surrounding an iconic supertall often see. The real money isn't necessarily made inside the supertall itself, it's made when developers jack up the real estate prices, hotel rates, and commercial rents of all the surrounding shorter buildings, simply because those buildings now have a premium, front-row view of the shiny new iconic landmark. It's just a fascinating, delicate balance between harsh engineering reality and boundless human ambition. So I'll leave you with this final thought. Next time you look up at your city's skyline, ask yourself, are you looking at smart structural logic or pure architectural ego? Thank you so much for joining me for this explainer. I really hope it completely changes the way you look at the concrete and steel giants all around us. Keep learning, keep questioning the world around you, and I'll catch you next time.